Quantum Mechanics in 4 Hours. This is the first of 4 videos. Hello, thank you for joining this class. My name is Walter Urbaniak. I'm a retired computer networking engineer. I have an interest in physics and particularly quantum mechanics, but I'm not a physicist and not a professor. This short course is a 4-hour introduction to quantum mechanics. This class is targeted at people who are not physicists but have an interest in physics. The transcript for these lectures is available as a PDF. The link is available in the description of the YouTube video and also here. tinyurl.com, QM in 4 hours. The course is divided into 4 videos, of which the first is the longest, about an hour and a half. The material is divided into 37 sections. After any section, you could pause and resume at a later date. I am reading from my script here, and I'm going to show you the script as I read it. You don't need to follow along the script. It'll be clear to you when I'm showing a diagram or going over an equation. But for some people, they may find it helpful to be able to read along, so I'm providing that. This course is a reduced, restructured version of a 17-hour course, Quantum Mechanics for Everybody, that I created and published to YouTube in 2019 and 2020. The playlist for that longer course is here at this link. That course consists of 4 segments: a 40-minute introduction to the series, 11 hours of history before quantum mechanics, a history of the cracks in classical physics that led to the need for quantum mechanics. You do not need this material in order to take this current course. However, if you come to feel that you need this historical introduction or that it would benefit you, it's available to you. 8 hours of the spatial aspects of quantum mechanics in more detail than we will cover in this new course. And 9 hours of the spin state aspects of quantum mechanics in much more detail than we will cover in this new course. But in this present course, we will cover much of the material of those 17 hours of quantum mechanics, but not the 11 hours of history. Expectations. You don't need to follow and understand every single point of these lectures in order to begin to see the larger picture and what quantum mechanics is. You don't need to take a lot of notes as the lecture scripts are available for download. So you may want to download them. You might want to print them and take notes on there rather than taking too many notes by hand. I don't expect that you have a strong background in classical physics or that you remembered what you learned long ago. When we need to know something, I'll explain what we need to know. We'll use as little math as we can, but I will need to use calculus and differential equations. But you can trust my results if you've never taken calculus or if you don't remember it. What is quantum mechanics? As of 1913, there were several cracks in otherwise brilliantly successful classical physics. Classical physics from 1500 to 1900 was such a complete, cohesive understanding of nature that explaining the cracks would ultimately require not minor adjustments, but a full-blown revolution, quantum mechanics, that would open our eyes to amazing aspects of our universe and reality. Quantum mechanics is the physics that describes the behavior of matter on a small scale, small as in the size of atoms or smaller. On that scale, physics is much different than classical physics. But now we know that quantum mechanics also affects our macroscopic reality in many interesting ways. Some quantum mechanical phenomena extend to 100 kilometers or more, and we can shine a laser beam from Earth to the Moon. But what is classical physics generally that quantum mechanics is different from? We will take classical physics to be the physics that was known and understood right up to 1900, acquired from scientific observation beginning around 1500. Classical mechanics describes how objects move, Newton's laws, position, velocity, acceleration, force, momentum, energy. Classical mechanics must be replaced with quantum mechanics on the scale of atoms or smaller. Classical physics also includes optics, electricity, magnetism, electromagnetic waves, thermodynamics, and the kinetic theory of gases. This introductory course will not touch on how these change as a result of quantum mechanics. Around 1900, a physics professor said that physics is complete. There is no longer really a reason for students to become physicists. There's nothing more to discover. He was 99% correct at the time, yet totally wrong. In a short time, there would be 3 revolutions in physics, unforeseen in 1900, one of which is quantum mechanics. Physics, reality, and the universe turned out to be a lot more interesting than was understood in 1900. If I look out my window, I see blue sky and green leaves on the trees. The blue sky can be explained by classical physics. But why leaves are green requires quantum mechanics. Why should someone learn quantum mechanics? Well, there's different reasons. Classical physics says that the electrons of atoms should collapse into the nucleus of the atom in a trillionth of a second. And then the Earth should collapse. Maybe you'd like to know why this does not happen. Quantum mechanics governs atoms, why they don't collapse, atomic size, energy levels, electron orbitals, bonding of atoms in a molecule, bond length, bond energy, vibration of bonds, rotation of molecules. So it directly relates to and results in chemistry, and therefore biochemistry and life. But it also relates to materials in general. Some of the properties that are governed by quantum mechanics in the atom make their way to materials properties on the macroscopic scale. The density of materials, the strength of materials, stiffness, whether a material is a conducting metal or an insulator or a semiconductor, whether a material is transparent or opaque or glows in the dark, its color, magnets, lasers, these all relate to quantum mechanics. Aside from these, quantum mechanics is weird, complex, novel, mysterious, and outside our everyday experience. Quantum mechanics does not make sense to our understanding of the macroscopic world as we have observed it since our childhood. Yet all experiments that have been done show that reality and the universe are governed by quantum mechanics at the small scale, and the macroscopic world inherits some of its characteristics. Modern quantum technologies such as quantum computing and quantum communication are also interesting, though beyond this course. This course and our approach. For our purposes, we can consider that quantum mechanics is needed to properly explain atoms and emission and absorption of light, though it does much more than these. This course is a very brief introduction to quantum mechanics for a single, non-relativistic particle, including Schrödinger's matter-wave equation, energy quantization of bound states, wave functions, superposition states, measurement, and other topics. We will get some insight into how quantum mechanical solutions differ from classical mechanics. My intention is that all of this material is correct and not dumbed down, but this is not a complete course in quantum mechanics. We will learn from the simplest possible bound state in one dimension, a particle permanently contained between two impenetrable walls. The particle can only have certain specific discrete values for kinetic energy. We will explore and use Schrödinger's wave equation for matter waves. Before jumping into the material, let me give you a roadmap of the material we'll cover in this course. We will start with a classical particle in a box. Then we will do light in a cavity modes. Then Planck's constant h and h bar, which I'll explain later. We'll do a quantum mechanical particle in a box. We'll look at the ground state and the 0-point energy for particle in a box. We'll look at transitions between energy levels, photon absorption and photon emission. Then we'll ask, is a heavy particle in a big box classical? And it is. We'll look at energy eigenfunctions for particle in a box. We'll ask, what is the wave function? What does it represent? We'll look at two other potentials, so not particle in a box, simple harmonic oscillator and hydrogen atom. We'll only look at them superficially to see how they're different than particle in a box. We'll look at the classical wave equation, and we will develop the quantum mechanical wave equation for matter waves, the Schrödinger equation. We'll look at curvature of the energy eigenfunction and see how it relates to kinetic energy. We'll look at operators, expectation value, uncertainty, and Heisenberg's uncertainty principle. Then we'll go back to particle in a box in one dimension and use what we've learned to explore more about particle in a box. We'll look at classically forbidden regions and tunneling through a barrier. Then we'll ask, why are the energies of bound states quantized? Superposition states for particle in a box in one dimension, superposition state expectation values, and a simulation of particle in a box in one dimension with angular momentum, and then intrinsic spin angular momentum. We'll look at multiple particles, the tensor product, and entangled states. We'll look at identical particles and the Pauli exclusion principle. We'll talk very briefly about modern quantum mechanical technologies. We'll look at the case of Schrödinger's cat. At the end of the final lecture, I'll give you a little more information about how to learn more about quantum mechanics. Now we'll look at a classical particle in a box. So not quantum mechanics, a regular classical mechanics particle. We can learn a lot about quantum mechanics and how it is different than classical mechanics, while minimizing complexity and using the simplest math, by looking at an idealized problem involving a single non-relativistic particle with mass m and traveling much slower than the speed of light, where there's no forces on the particle other than bouncing off two rigid walls, and treating the problem in only one dimension, the x direction. Consider a classical point-like particle or a finite-sized object and its center of mass permanently confined between two ideal, rigid, impenetrable walls located at x equals 0 and x equals L. Either the particle is stationary at rest at some location, or it is moving, in which case it will forever bounce off the walls. The walls are perfect, ideal, elastic, so no energy gets lost, so the object will forever bounce between the walls. If the particle is at rest at some time t, then it will remain at rest at all future times because there's no force on the particle, so nothing to accelerate it. So here's a classical particle at rest. Zero kinetic energy. The horizontal axis is distance, x equals 0, x equal L. Beyond x equal L and beyond x equals 0, the cross-hatched line shows that that's a rigid, impenetrable wall. The vertical axis here is energy. This horizontal line is zero energy. The only energy here is kinetic energy, and so if a particle has zero energy, it has zero kinetic energy. Here I'm showing a particle with zero kinetic energy. It's at some position x, and it has no kinetic energy, no velocity. There's nothing to accelerate it, so it will stay there forever. So that's a classical particle at rest. We will learn later that in quantum mechanics, unlike classical mechanics, no particle can ever be at rest, localized to a definite position in space, and remain there. Now, back to classical mechanics. Let's say that at time t equals 0, the particle's position is at the left wall, x equals 0, and its velocity is precisely v. So it's at the left wall, moving to the right, toward the right wall. Here's a picture where now the vertical axis is time, not energy. So at time t equals 0, the particle is at the left wall, x equals 0. It has just bounced off and it is moving to the right, moving to the right, moving to the right, until it eventually hits the right wall, bounces off, moves to the left, bounces off the left wall, bounces off the right wall, the left wall, the right wall, and so on. And it will do that forever if the walls are ideal and perfect, and the particle is a perfectly rigid particle. We will learn later that in quantum mechanics, unlike classical mechanics, it is impossible to simultaneously determine, measure, or know the position and velocity of a particle in that direction perfectly precisely. We can know them somewhat, but we can't know them perfectly at the same time. So we can't have anything like this situation of knowing that a particle bounced off the left wall and bounced off the right wall in quantum mechanics. In classical mechanics, the classical particle, it'll travel the distance L between the walls in time capital T equal the length between the walls divided by the velocity. It'll bounce perfectly elastically off the rigid right wall, losing no energy. It'll travel to the left with the same magnitude of velocity, and it will continue forever bouncing between the two walls without losing any energy. So here's a diagram, position and energy, for a particle that has some kinetic energy. it has a definite value of kinetic energy at all times. It might be traveling to the left at some time, traveling to the right at another time, but it always has the same amount of kinetic energy for all time, for a classical particle. Averaged over time, the particle has an equal probability to be anywhere within the box. However, classically, the particle has a definite position at every value of time, so we don't think of its position as a probability at all because it's definite. We can determine its position at any time. The momentum of the particle is mass times velocity. So it's represented by lowercase p equals mass times velocity v. Except at the instantaneous moments of bouncing off the walls, the magnitude of the momentum is constant because the magnitude of velocity is constant. Because there's no force on the particle other than bouncing off the walls, the potential energy experienced by the particle in between the walls is zero. The kinetic energy of the particle is 1/2 mass times velocity squared, which is the same as the momentum squared divided by twice the mass. Classically, the particle could have any value of initial velocity, so any non-negative values for magnitude of momentum and kinetic energy. We will learn later that in quantum mechanics, unlike classical mechanics, the total energy allowed for a particle bound by a potential is quantized, not a continuous or arbitrary value. Now we'll switch to a different classical physics phenomena, but not classical mechanics. Light in a cavity modes. Light and electromagnetic waves are classical phenomena, classical optics and electromagnetism. However, the possible energies that wave modes can take on is quantized, not continuous, in cases such as restricting the light to a cavity, for example, black body cavity radiation, or interacting with matter such as in the photoelectric effect, or absorption or emission of photons by an atom or a material. Photons have zero rest mass, and so they're not covered by non-relativistic quantum mechanics or the Schrödinger equation. However, the quantum mechanical matter wave solution for matter particles in a particle in a box, the solution is very similar to Max Planck's 1901 solution for light waves in a black body cavity. So we'll look at that. Light constrained to a one-dimensional cavity of length L is a standing transverse electromagnetic wave. The electric field and magnetic field oscillate in time, while their peak amplitude profile does not move in space. Oscillations of piano strings and guitar strings are also standing transverse waves. The electromagnetic cavity waves are constrained to definite wavelengths such that an integral number of half wavelengths equals the cavity length L. This then allows the electric field to remain zero at the conducting cavity walls. The conducting metallic walls for the electromagnetic cavity modes are different than the ideal impenetrable walls for constraining a particle with mass, whether classical or quantum mechanical. So the walls are different, but some of the mathematical results are going to be the same. Here's a plot of the waves of different cavity modes in the cavity. The cavity starts here on the left. There's a conducting wall here, and it ends on the right here where there's another conducting wall. So don't think of this as extending beyond the left or beyond the right. There are conducting walls here that terminate all of the electromagnetic waves. The cavity modes are identified by the number of half wavelengths that are present in the cavity. For n equals 1, there's one half wavelength present in the cavity. The electric field is 0 here, it goes up to its peak value and goes down to 0 here, 1/2 wavelength. For n equals 2, we have 2 half wavelengths, or 1 complete wavelength in the cavity. 0 up, 0 down, 0. For mode 3, we have 3 half wavelengths. 1/2 wavelength, 2nd half wavelength, 3rd half wavelength. And we can have an infinite number of modes. The wavelength gets smaller and smaller. The frequency gets higher and higher. It can have 30 modes, 60 modes, 120 modes, 240 modes. There's no end. There's a countable infinity of the number of modes in the cavity. Let's consider a single cavity mode labeled N with electric field. So the cavity is in the X direction, and we'll say that the electric field is oriented in the Y direction, with peak magnitude electric field E sub n, which we'll take as being due to just a single photon of that mode in the cavity. For an actual black body, there would be very many modes would be active, and each mode would be populated by many photons. So we're just considering a single photon. If we solve Maxwell's equations, we will find the following formulas for the electric and magnetic field standing waves. The fields are standing waves. There's a position dependence, sine kx and cosine kx, multiplied by a time dependence, cosine omega t, sine omega t. These are standing waves. The wavelength, lambda sub n, is twice the length of the cavity divided by the mode number, which can take on values 1, 2, 3, up to plus infinity. The wave number, k sub n, is 2 pi over lambda, so it is pi over length L times mode n. Angular frequency omega sub n is pi times the speed of light over the length of the cavity times mode n. The frequency, f sub n, is the speed of light over twice the length of the cavity times mode n. Note that electric field and magnetic field standing waves, they're out of phase in time and space. Here's its sine kx, here it's cosine kx. Here it's cosine omega t, sine omega t. So out of phase, because it's a standing wave, not a traveling wave. The electric field is 0 at x equals 0 and x equals L at all times. That's because the sine wave is always 0 for x equals 0, and when x equals L, we have sine of k sub n L, which is pi over L times n times L, which is pi times n, with n being an integer, so that is always 0. So the electric field is 0 at x equals 0 and x equals L at all times. The electric and magnetic fields could equivalently be expressed as the sum, the superposition, of two traveling plane waves of equal amplitude traveling in opposite directions, plus and minus x. Now, So far, that is all classical physics. That the allowed wavelengths, wave numbers, and angular frequencies take on definite values, not arbitrary continuous values. For a cavity, that's a classical result. However, when we consider the amount of energy that can be in each mode, then we get Max Planck's non-classical result, that the energy in a given cavity mode n can only be an integer times the definite quantum of energy for the mode. The quantum of energy for mode n is h, Planck's constant, times the frequency for that mode, or h bar omega sub n, where omega is the angular frequency. H bar, this funny symbol with a little tiny slash in it, is always called h bar. Its title is the reduced Planck's constant, and it equals Planck's constant over 2 pi. It appears everywhere in quantum mechanics, so h bar appears more frequently than Planck's constant itself. So if we use either of these formulas from up above, we get that the energy for a single photon of a single mode is Planck's constant times the speed of light divided by twice the cavity length times the mode number, where the mode number is n equals 1, 2, 3, and so on. So the energy is quantized, and we call this photons. Here are values for Planck's constant, although you're not going to be using the values and doing any math. I will do some math for you. The units for Planck's constant, h, is the same as the units for h bar, and it's in energy times time. If we're looking at macroscopic problems, we'll use energy in joules. So Planck's constant will be joule seconds. But when we're talking about electrons and atoms, the unit of energy that we'll use is electron volts, and so the units for Planck's constant are electron volt seconds, or eV seconds. If you're not familiar with joules or electron volts, that's fine. You don't need to be really. Sometimes it's useful to have the constant that is Planck's constant times the speed of light, and the units for that are electron volt meters. Now, Planck's constant has dimensions of energy times time, such that multiplying by frequency, which is 1 over time, gives energy. That's what makes E equals HF work. But it turns out that is also the dimensionality of angular momentum and position times momentum, and these are important to quantum mechanics. You're not familiar with the unit of electron volts, but visible light photons have an energy of 2 to 3 electron volts. So you can at least imagine the scale of that energy unit. Physicists have determined the value of Planck's constant very precisely. Planck's constant is a universal physical constant. As far as is known, it has the same value everywhere in the observable universe and at all past times. So galaxies 10 billion light years away, whose light started out 10 billion years ago, that light was emitted from an atom, and Planck's constant for that emission is the same as the value here on Earth. We will consider a single standing wave cavity mode n populated by a single photon of energy E sub n equals hc over 2 length 2L times n. The standing wave photon carries no momentum. It's a standing wave. A traveling plane wave photon, not a cavity mode, moving in the plus x direction with photon energy E sub n, it would have momentum p sub n being energy over speed of light for a traveling wave photon. Let's graph the single photon's allowed energies for the cavity modes. So horizontally we have position in the cavity from x equals 0 to x equals L. Vertically we have energy. We could have no photon in some mode, in which case there would be no energy, but if we have a photon, then the photon can only carry certain energies depending on the mode. Mode 1, the energy is hc over 2L. For mode 2, it's twice that. For mode 3, it's 3 times that. For mode n, it's n times that. So the photon energies in this cavity are quantized. Planck's constant h and h bar. If you have not already done so because of taking one of my other courses, I strongly recommend that you pause this lecture and watch one of my 2 lectures, short or long, about Planck's constant. And they are at these URLs. Here's the URL for the short 13-minute lecture. Here's the URL for the longer 94-minute lecture. These will give you a lot of information about Planck's constant, its dimensionality, its units, its values, and also the energy values that we're going to be using, electron volts. You don't have to pause this video and watch those lectures. It's optional. But if you want to get the most out of this course, you will at least watch the short video. A quantum mechanical particle in a box. Like cavity modes of electromagnetic radiation, but unlike a classical particle, a quantum mechanical particle of non-zero mass constrained, bound within an impenetrable box can only take on definite quantized values of total energy. These allowed values for total energy are called energy eigenvalues. The energy eigenvalues are found as the solutions of Schrödinger's matter-wave equation, which we will introduce in a later section. Let a non-relativistic particle of non-zero mass m be permanently confined, bound between 2 ideal, rigid, impenetrable, hard walls located at x equals 0 and x equals L. We treat this as a one-dimensional problem. We ignore the y and z directions. We call this problem particle in a box, in particular particle in a box in one dimension, which we will sometimes abbreviate PIB. Later, we'll be able to show that Schrödinger's equation for this problem has solutions with the following definite quantized total energy values. E sub n equals h bar squared pi squared n squared over 2ml squared, where n takes on integer values 1, 2, 3 up to plus infinity. This was h bar. This can also be re-expressed as Planck's constant h squared n squared over 8ml squared. And it can also be expressed as quantity hn over 2l squared divided by 2m. We'll see later why we should want to do that. This is only kinetic energy, And this kinetic energy is equivalent to a classical particle with momentum p sub n equal hn over 2L. That's the value in this quantity. So this energy would be p squared over twice the mass, which would be the correct classical equation for classical kinetic energy. So this is a quantum mechanical energy, but we can understand it in terms of a classical momentum. More on this later in the class. Now let's graph the energy levels for a particle in a box in one dimension, which is also called infinite square well. Horizontal is a position 0 to L. Cross-hatching means impenetrable wall at 0, impenetrable wall at L. Vertical axis is energy. This solid black horizontal line is zero energy, zero kinetic energy. The particle cannot have that. The lowest energy it can have is E sub 1, which is h squared over 8ml squared. E sub 1 is called the ground state energy. The second level, energy level, has 4 times the ground state energy. The third energy level has 9 times the ground state energy. The fourth energy level has 16 times the ground state energy. The nth energy level has n squared times the ground state energy. So, the energy eigenvalues for a particle in a box are quantized, as are the photon energies for the cavity modes of a black box. But the energy values are much different. The photon energies are equal to the photon momentum, hn over 2L, times the speed of light, whereas the particle with mass has kinetic energies equal to the momentum squared divided by twice the particle's mass. The photon energies are p sub nc, whereas the particles with mass has kinetic energy equal to p squared over 2m for a particle in a box. The difference is that the photon is massless and always travels at the speed of light, whereas the particle has mass, and we're only considering non-relativistic energies, where the kinetic energy is much less than the rest mass energy mc squared, and we're not counting the rest mass energy into total energy. So that's why the particle with mass has kinetic energies that are proportional to the momentum squared. Ground state energy and zero-point energy. For any quantum mechanical bound state, there is a state called the ground state with the lowest possible energy that the particle can have for that case or problem. Bound states that have higher energy than the ground state are called excited states. For a particle in a box in one dimension, the lowest possible value for n is 1, and the ground state kinetic energy, E sub 1, is h bar squared pi squared over 2ml squared. This is also called the zero-point energy. This minimum kinetic energy is not zero. This is a general result for bound states. For any bound state, the minimum allowed kinetic energy, the zero-point energy, is greater than 0. The particle cannot ever be at rest, localized to a definite position in space, and remain there. Transitions between energy levels, photon absorption and emission. A bound system with multiple discrete energy levels can transition from one energy level to another. This is sometimes called a quantum jump, but don't think of this as a jump in position. This is a jump in energy. To jump or transition from a lower energy level to a higher energy level, the system must absorb the precise amount of energy needed from the external environment, typically absorbing a single photon with the right energy, frequency, and wavelength. So to jump from level 1 to level 2, the system, the electron, the atom, must absorb one photon with exactly the right energy to increase the energy from level 1 to level 2. For particle in a box, the hard walls are impenetrable to the particle in the box, but they're transparent to photons entering or leaving the box. So don't think of those as also walls of cavity radiation. They're not. They're two separate mathematical problems. To fall or drop or transition from a higher energy level to a lower energy level, the system must emit the precise amount of energy to the external environment, typically emitting a single photon with the right energy, frequency, and wavelength. So the system starts with energy 2, it emits the right energy of photons, and it drops to level 1, and this is called spontaneous emission. In a bit, we will talk about how long it takes before spontaneous emission occurs. But it also can happen that a photon emitted by one atom can stimulate the immediate fall or transition of another atom, and then another atom, and so on. This is called stimulated emission and was predicted by Einstein. So if the electron in one atom is in level 2, and it would eventually spontaneously emit a photon and fall to level 1, if exactly the right energy and frequency of photon came along, then rather than waiting an arbitrary probabilistic amount of time for spontaneous emission, this atom will be stimulated to immediately drop into level 1 and emit its own photon, which will be in phase with the original photon. This is called stimulated emission. Stimulated emission produces high-intensity coherent light. Coherent means all of the photons are in phase. They're the same wavelength, frequency, energy, and they are in phase. They're going in the same direction and they are in phase. And stimulated emission is the basis for lasers, first invented in 1960, and used in our CD players in 1982 and our DVD players in 1997, and also the basis for high-speed telecommunication links in the internet and telephone system. LASER is the acronym for light amplification by stimulated emission of radiation. Here's a picture of laser lights of different colors. Now, spontaneous emission must occur from any excited state. An excited state cannot remain forever excited. Eventually, it must emit a photon and drop to a lower level. Excited state natural lifetimes vary from a small fraction of a second to 1,000,000 years. Transitions with lifetimes longer than a fraction of a second are sometimes called forbidden transitions or even extremely forbidden transitions. These transitions, they're not impossible, but they cannot use the simplest, fastest transition mechanism, and so they take longer. Fluorescent glow-in-the-dark patches that glow for hours, they rely on a forbidden transition between energy levels in an atom. There's an extremely forbidden transition between two energy levels of a hydrogen atom that has a lifetime of 1,000,000 years in the near vacuum between the stars and between galaxies. And those photons that get emitted and absorbed are important in radio astronomy. Now, is a heavy enough particle in a big enough box classical? And it is. Let's see that. What do the quantum mechanical energies for particle in a box mean for macroscopic objects such as a baseball? It turns out that quantum mechanical results tend to classical results when particle mass m is large enough, and confinement distance L is large enough. Note that both of these are in the denominator, ml squared. So as they get large, the denominator gets small, and we will see that the spacing between energy levels gets smaller. So when m is large and confinement distance L is large enough, we can use classical mechanics to solve these problems. Let's explore this for particle in a box in one dimension. If the spacing between adjacent energy eigenvalues is small enough, then the energy values will seem continuous and classical mechanics may suffice. The difference in kinetic energy between state n+1 and state n, we just use this formula when substitute n+1 and subtract n. So the difference between two adjacent energy levels is h bar squared pi squared over 2ml squared times the quantity n+1 squared minus n squared, and we can use math to simplify that to be 2n+1, and we can divide by the nth energy level and we get 2n+1 over n squared. And we're going to be interested in cases where n is much greater than 1, and so this is approximately 2 over n. The energy values will seem continuous for a particle in a box in one dimension when n is very large compared to 1. The energy values will seem continuous. The delta E over E will seem continuous. Now, to make an assessment, we should look near a practical value of kinetic energy, not at the 0-point energy, because the world around us is not at the 0-point energy. Let's say that a particle has a kinetic energy that it would have if it were in thermal equilibrium with the environment at absolute temperature T. For this problem, we'll take its thermal energy as 1/2 kT, where K is Boltzmann's constant. At room temperature, 300 Kelvin, if you know Boltzmann constant, you can multiply it out, and the kinetic energy will be 0.026 electron volts, 1/40th of an electron volt. Well, let's plug that in and solve for the value of n for that. When we substitute it in, we get that n will be ml squared for whatever object we're talking about in whatever confined box we're talking about, divided by 1.3 times 10 to the minus 47 kilogram meters squared, and the square root of that. We can plug that into the delta E over E formula, and we get approximately square root of 5.3 by 10 to the minus 47 kilogram meters per squared divided by ml squared, when n is much greater than 1, which is the case we're going to be concerned with. Now, sticking with room temperature, let's take a concrete example. Let's confine a small protein weighing 1.4 times 10 to the minus 23 kilograms. Let's confine it to a small box, 20 nanometers, so 20 billionths of a meter. An atom is about the size of an angstrom, a tenth of a nanometer. So you could think of this box as being, 200 atoms wide. So we're confining a small protein to a box that's 200 atoms wide. Let's look at the delta energy over energy. For this, if we were to plug these numbers into here, we would find that delta E over E is about 1/10,000th. So the spacing between energy levels is 1/10,000th of the energy level itself. And so the motion of that protein within the box should be pretty classical because this is a pretty small amount. Now, it could be that this protein wouldn't even fit in that box. I haven't checked that. But we can see that if there was something with this mass confined to that box, its motion is probably pretty classical. However, and for objects with higher mass and less confinement, a virus particle, a bacterium, a baseball, they'll be pretty classical. But a smaller object, more closely confined, an oxygen molecule confined to a much smaller box, a 3 angstrom, a 0.3 nanometer wide box, so just a little bigger than the molecule itself, that's going to have a delta E over E of about 1/10th, and so its kinetic energy is still pretty quantized and quantum mechanical in that box. And even lighter particles like an electron with smaller confinement, such as an electron confined within an atom, they will not be classical. We have to use quantum mechanics for them. Energy eigenfunctions for particle in a box. Like cavity modes of electromagnetic radiation, but unlike a classical particle, a quantum mechanical particle of non-zero mass constrained bound within an impenetrable box, it has states of definite quantized values of kinetic energy and total energy. Those energy eigenvalues and the corresponding descriptions of the state of the particle, called the energy eigenfunctions, they are found as the solutions to Schrödinger's matter wave equation, which we will introduce in a later section. For a particular problem, the general solutions to the Schrödinger equation are called wave functions. And they're a function of space and time. Energy eigenfunctions are a special important subset of the general wave functions. All wave functions can be expressed as superpositions, linear combinations of the energy eigenfunctions. The energy eigenfunctions have a definite, discrete energy, but in general a system could be in a superposition of energy states, and we will talk about that later. For energy eigenfunctions, the time dependence can be separated out from the spatial dependence, and we will cover the time dependence later. Let a non-relativistic particle of non-zero mass m be permanently confined, bound between two ideal rigid impenetrable walls located at x equals 0 and nl, particle in a box. Treat this as a one-dimensional problem, ignore y and z. Later we will show that Schrodinger's equation for this particle in a box has solutions with the following definite spatial energy eigenfunctions, which we represent with Greek lowercase letter psi, and there will be different possible energies and eigenfunctions, and we'll index those by integer index n. So energy eigenfunction lowercase psi sub n, which will be a function of position, x. For now, don't be concerned with what the function represents physically. We'll talk about that later after we see the form of the functions. So energy eigenfunction psi sub n of x is going to be 0 for x less than 0, beyond the left hard wall. 0 for x greater than L, beyond the right hard wall. In between the two hard walls, it's going to be square root of 2 over L times the sine function of k sub n times x, where quantum number n is going to range from 1, 2, and 3, and k sub n is going to be 2 pi over the wavelength. The wavelength is going to be twice the length of the cavity divided by n, so the wave number k sub n is going to be n times pi over L, and the energy eigenfunction with it between the walls is going to be square root of 2 over L sine n pi x over L. This gives the matter particle wave function an integer number of half wavelengths within the allowed region, the same as we did for light waves in the black body cavity. Note that energy eigenfunction psi sub n is 0 for x less than or equal to 0, and for x greater than or equal to L. Because if we plug in L here, we get L over L and we get n pi, and n is an integer, and sine of n pi is always 0. So the energy eigenfunction is 0 at and beyond the two hard walls at all times and for all values of n. Beyond the walls is called a completely forbidden region. Now, perhaps surprisingly, perhaps not, the allowed values for wavelength lambda sub n and wave number k sub n for this particle with mass in a one-dimensional box are identical with the values for an electromagnetic cavity wave that we covered earlier. The sine k sub n x spatial variation of the energy eigenfunction, psi sub n of x, matches the spatial variation of the cavity mode electric field. However, we'll see later that the time dependence of the matter particle energy eigenfunction is and must be different than for the electromagnetic standing wave. We'll see that later. That's an important difference between matter and light. Let's look at the energy eigenfunctions for the three lowest energy eigenvalues. We could do this on three separate plots, but it's common to show them on a single plot, shifted vertically. So horizontal axis is x. Here we have x less than 0, and in each case the wave function is 0. Here this green horizontal line is 0. This blue horizontal line, that is its 0. This red horizontal line is its 0. Likewise, there's 0 beyond x equals L, so beyond the right wall. But between the two walls, For the n equals 1 ground state, we get a half wavelength. For the n equals 2 excited state, we get 2 half wavelengths, or 1 whole wavelength. For n equals 3 excited state, we get 3 half wavelengths within the cavity. For the n equals 2 and n equals 3 in all higher modes, there is a zero crossing, or there is at least one zero crossing or node in between the hard walls. In fact, for mode n, there will be n minus 1 nodes. These curves look like standing waves of a string, for example a guitar string, or the standing waves for light. Note that the value of the wave function outside the box is 0. Now, it's also common to show the energy levels and wave functions on the same graph. Here, horizontal is still space, but now vertical is energy, but it's only energy for these horizontal lines which are representing the energy levels of the different states. So energy for the green ground state energy, for the blue n equals 2 excited state energy. So everything in black is showing the box in which the particle is confined, which is the potential energy function for this particular problem. Horizontal axis is position, the vertical axis is energy for the horizontal line energy levels, but not for the energy eigenfunctions. The cross-hatching represents an impenetrable barrier. We can write the potential energy function, V of x. It is 0 between the walls and plus infinity beyond the walls. Now, if you object to infinite values, saying you can't have anything in physics that's infinite, then consider them to be arbitrarily high, finite, positive values. The three colored horizontal lines, they're the lowest 3 energy levels, E sub 1, the ground state energy, E sub 2, and E sub 3. The 3 colored sine waves are the 3 lowest energy eigenfunctions. Psi sub 1 of x, the ground state energy eigenfunction, psi sub 2, and psi sub 3. For bound state energy eigenfunctions, as we go from one energy level, E sub n, to the adjacent higher energy level, E sub n plus 1, the energy eigenfunction gets one additional node, one additional zero crossing in space. The additional spatial node means that the wave function becomes more compressed or scrunched in space as we go up from n to n plus 1. This tightens the spatial curvature of the wave function, and that curvature is a manifestation of the increased kinetic energy. The momentum distribution for this state also increases in momentum. We can appreciate these properties better after we examine the Schrödinger equation. So, as we go from n equals 1 to n equals 2, we go from 1 half wavelength to 2 half wavelengths. So we've scrunched in twice as many half wavelengths, and in order to do that, there's more curvature here than here, and that curvature is related to kinetic energy, which is why this state has higher energy than the ground state. For three-dimensional problems, nodes of the wave function are two-dimensional surfaces, such as planes or spherical surfaces. Now, we've spent a lot of time on energy eigenvalues and a little time on energy eigenfunctions, These are very important solutions and building blocks. However, we'll see later in the course that some of the most interesting and useful solutions will be time-varying superpositions of the building block states. At this point, that's all I can say is that energy eigenvalues and energy eigenfunctions are very important, but these are the beginning, not the end. Now, what is the wave function? We saw that the wave function was sine waves, but so what is it a wave of? When Schrödinger developed the Schrödinger equation for matter waves in 1925-26, he expected that the wave function represented the definite position of the particle. The classical wave equation for a water wave shows how the peaks and troughs of a water wave move in space and time. But in quantum mechanics, the matter wave is not a physical displacement wave like a water wave or sound wave, and it's also not an electromagnetic wave. Physicists were surprised that the quantum mechanical wave function is not like any classical wave, but rather it's probabilistic, not deterministic. It's a probability amplitude, not directly measurable, and also not directly a probability. We'll see that later. It's a probability amplitude that encodes probabilities for where the particle is located in space and time, the probability distribution for particle momentum values, and the probabilities for different total energy values for the particle. This was unexpected, disconcerting, unwelcome, and yet physicists learned how to use and interpret wave functions. The time-dependent wave function, which we always represent with a Greek uppercase letter psi, capital Psi, that is a function of spatial coordinates and time, psi of x, y, z, and t. When the wave function includes its time variation, it is always complex valued, taking complex numbers, not just real numbers, for its values. This is an unavoidable necessity of quantum mechanics. If you're not familiar with complex numbers and complex exponentials, and if you want to understand the time variation of wave functions later in these lectures, consider pausing this video and learning or relearning complex numbers and complex exponentials, which you can get from my video here or from Khan Academy videos. It turns out that the magnitude squared of the wave function tells us the probability density for the particle to be near a given point in space at a given time. Magnitude squared can be expressed this way, where the vertical bars mean magnitude and then it gets squared, magnitude of a number which could be a real number or a complex number, or equivalently it can be expressed as the product psi star psi, where the asterisk star represents the complex conjugate. So the complex conjugate of this complex valued function. Probability density rho for the particle to be near point xyz at time t is magnitude squared, so psi star psi, divided by the integral of psi star psi over all space. Now typically, and whenever we can, we scale the wave function by the appropriate factor to make the integral over all space in the denominator equal 1, meaning that one particle exists somewhere in all of space. In which case we say that the scaled wave function is normalized. We won't cover it, but there's also a formula for the probability for the particle's momentum to be near momentum value, p sub x, p sub y, p sub z, at time t. Energy eigenfunctions are special cases of wave functions. Their probability densities distributions are independent of time. For energy eigenfunctions of a one-dimensional problem, where we have normalized the eigenfunctions, the probability density rho for the particle to be near point x at any time is rho sub x is not a function of time. It is lowercase psi star of x times psi of x. For the particle in a box in one dimension, energy eigenfunctions, we already covered the energy eigenfunctions, so we can calculate the probability density rho for the particle to be near point x at any time. So rho sub n for quantum number n is a function of x, and it is 0 for all space to the left of the left hard wall, 0 for all of space to the right of the right hard wall, and between the hard walls it is 2 over L sine squared n pi x over L, where n ranges from 1, 2, 3 up to plus infinity. Now, if you integrate this over all x, you will get one particle occupying the state, probability 1, because I included this factor square root of 2 over L in front of the energy eigenfunction. I included that intentionally so that it would be normalized. Let's look at the probability distributions for the 3 lowest energy eigenvalues for particle in a box in one dimension. I'm plotting all 3 on one chart, but I'm spacing them vertically so we can see them more clearly. They all have 0 probability density of being beyond the box. The shape is sine squared, not sine, so the shape is a little different, different than the wave function. Here is the probability density for the ground state, for the n equals 2 state, which has a node in the middle of the box, the n equal 3 state, which has 2 nodes. The probability density is not a constant number between the walls. It is not 1 over L. The probability density varies in space, but not in time for these energy eigenstates. The probability density is different for different states. All states except for the ground state have one or more node between the walls where the probability density is 0. The particle will not be found at the node locations. This is all much different from the classical particle bouncing forever between the walls. The probability distribution for a quantum mechanical particle is not any kind of trajectory in time. Let's look briefly at 2 other potentials: the simple harmonic oscillator and the hydrogen atom. We're only going to look at energy levels here. Let's compare the energy spectrum of a particle in a box to 2 other potentials, which we're not going to solve. Here was energy levels for particle in a box, and they increased with n squared times the ground state energy level. For simple harmonic oscillator, the potential energy is a quadratic, a parabola. V of x equals 1/2 m omega squared x squared, this solid black parabola in space. It turns out that that is a magic potential which results in all of the energy levels being equally spaced. The energy levels are quantized. There is a ground state. Here they're indexed by an integer n starting with 0. This is the ground state energy. This is n equals 1, the first excited state energy. And the energies are all h bar omega, where omega comes from the quadratic potential, times n plus 1/2. The ground state energy is not 0. It does not have 0 kinetic energy. There is 0 point energy. Now, the hydrogen atom, 1 electron and 1 proton in the nucleus, it is a lot more complicated. The binding energy is attraction, electrostatic attraction between the negatively charged electron and the positively charged proton or nucleus. That results in a potential energy V of distance between the two. Distance r is proportional to -1/r, where at infinitely large separation the potential energy is 0. The electron can be infinitely far from the proton, and then it's like it has escaped. But as the spacing gets closer and closer to 0, the potential energy, this green curve, it gets more negative toward negative infinity. So this horizontal scale here is distance r. The vertical scale here is energy in electron volts. The green curve is potential energy. It turns out that all of the quantized energy levels for the hydrogen atom, they are on this blue curve, which is 1/2 the potential energy curve. There is a ground state quantized energy level, n equals 1. It is this purple dot, minus 13.6 electron volts. The first excited energy state is n equals 2. And it has 1/4 of the binding energy, minus 13.6 divided by 4. The third state has 1/9 of the ground state energy. The nth level energy is minus 13.6 electron volts over n squared. As n gets larger and larger, there's a countable infinity number of quantized energy levels. However, they all approach zero energy as n gets larger and larger. The simple harmonic oscillator and the hydrogen atom, they have no impenetrable walls in their potentials. They are an attractive potential. For a given energy eigenstate, the total energy is above the potential energy near the origin. So there's positive kinetic energy. If we look here, between here and here, the energy, the red line, is higher than the potential energy, which is the black solid line. So between here and here, there's positive kinetic energy. However, farther away, the total energy is below the potential energy. Here, the energy is here, the potential energy is here, so the energy is below the potential energy. In that region, the wave function is not zero, but it's a decaying exponential with distance from the origin. There's a non-zero probability for the particle to be at any given point in this classically forbidden region. So it's not a completely forbidden region, it's a classically forbidden region. We will revisit this later. This is the end of the first of 4 videos for this course.